Oh, there they are. They want a guest lecture. They're not sure when they want to jump in. But here we are with electrolysis, section 17.7. And electrolysis is used to do plating of jewelry, gold plating. So if you start with this, you can plate these using electrolysis to put gold onto silver. Kind of cool, huh? So, electrolysis. It's the reverse process of a galvanic cell, non-spontaneous. You fill in the blank, pause your screen, I'm about to fill it in. So delta G, oh, nope. All right, delta G is positive, not negative. Did you get tricked? I was thinking about E cell. E cell is negative because this is non-spontaneous. Okay, so we can have a galvanic cell and we apply energy to it and make it run in the reverse direction and it becomes an electrolytic cell. So normally, positive E0, just a regular old galvanic cell. This would be an electrolytic cell because it's running in the reverse, negative E0. And here we don't actually need a battery. It's almost like this is charging the battery. We're charging the battery up, and now the battery is getting used. This is sort of how rechargeable batteries work. You plug them into your wall, and they get recharged by the electricity in your wall. And then you, oops, no, this is where, no, they get, I'm saying this backwards. They're getting recharged here. Never mind, this is not like that. Okay, so we have two cells here. One of them is galvanic and one is electrolytic, and they're kind of hard to see. But if you look up the zinc and the copper, and we see we're going in this direction over here, and the voltage is 1.1, and over here we have a power source that's applying a voltage that's 1.1. So pause and write in what you think, and I'm going to write it on here myself. All right, so what's the big deal about these cells? Well, actually, it's just dimensional analysis. We can do some calculations about what happens in electrolysis. You need to know an amp is a coulomb per second, and a Faraday is a mole of electrons, which has 96,500 coulombs of charge. So, let's talk about jewelry. How long will it take a current of 5 amps to plate out 10.5 grams of gold onto silver if the solution has gold 2 ions? So this is totally dimensional analysis. You don't even have to think about stoichiometry. I'm going to show you the solution in just a moment. We're going to do this way. We start with our gold, and we just see what when we convert. It's okay to make some noise. We can go grams to moles. We always do grams to moles. And remember, this amps will be coulombs per second. And you look at this, you say coulombs can get us to moles of electrons. So if somehow we can get from grams to moles of electrons, then we could go to coulombs, and from coulombs we can go to time, which is what we're looking for, how long. And notice, grams, we can go to moles, and for a mole of gold, notice we need these 2 plus, we need 2 moles of electrons. So here we go, grams to moles, easy. Gold to gold, it's a mole to a mole, and we needed 2 moles of electrons because of that 2 plus. These problems are so easy. There's that Faraday. A mole of electrons has 96,500 coulombs of charge. What just happened? We're going to pause a second. Sorry about that. I don't know what happened there. So we had our 96,500 coulombs per mole of electrons. And then here's our amps. We were told 5 amps. That's 5 coulombs per second. It's the definition of an amp is a coulomb per second. So if I have 5 amps, I have 5 coulombs per second. And I can turn it upside down and use it as a conversion factor. Beautiful. There you go.
Hi, everyone. So we have some more problems. Question number 2. How long will it take a current of 7 amps to plate out 15.2 grams of iron from Fe3+?
So you can try to figure out who that was. So now you just want to look. We have amps and we have grams. We can go grams to moles. Moles to moles, moles to moles. We'll need 3 moles of electrons this time. We have our 96,500 coulombs per mole of electrons. If you want to solve this on your own, go ahead, but pause because here we go. Very simple. Grams to moles. mole, 3 moles of electrons to 1 mole of Fe3+. And then we have our little mole of electrons. We can always go to coulombs. Here's our amps, 7 coulombs per 1 second. Okay, you don't need to convert all the way to hours. I just thought it was interesting. This is a lot of seconds. You could leave it in seconds or go all the way to hours. All right, this problem is different. This time I'm asking for current, so I'm going to need coulombs per second. Oh, here's my time right here. I can get seconds there. So somehow this is going to give me coulombs. Well, if you look right up here, I can follow this model for getting to coulombs. Again, it's just conversions. Have a wonderful evening. So we start with our grams, grams to moles, moles to moles. We need 2 moles of electrons because of the 2+. And then a mole of electrons is 96,500 coulombs. Here's our coulombs. We're going to divide by the seconds to get amps. And there you go. Hopefully I calculated that correctly. And if you want to do these on your own, just pause. Once you see the question, go ahead and pause or listen and follow along with me. This time we have time and current. So current, we know, is coulombs per second. So this is going to be 2.5 coulombs per second. We know we can get seconds from this. So if we look at seconds and coulombs per second, that gives us coulombs. And we're trying to get to the mass of iron from iron 3 ions. So we're just going to multiply these together. And again, pause if you can figure this out on your own. We'll get coulombs. We'll go coulombs to moles of electrons to moles of iron, and then moles to grams. And there you have it. So first we have to convert our 15 minutes to seconds, and our amps, coulombs per second, seconds cancel. We know our conversion from coulombs to moles electrons, and because of the 3+, 3 moles electrons to 1 mole of Fe, 1 to 1, and then moles to grams. Okay, looks like that's all we have on that one. Oops. Last topic. Okay, electrolysis and determining half reactions that will occur. So these are non-spontaneous, and electrolysis happens typically in water, and we always have to check the ions and the water to see which half reactions will give us the most spontaneous reactions. Okay. So let's do a problem. We've got potassium iodide in water, and we need to determine E cell and the half reactions. So first you have to look at your cell potentials. We had potassium iodide. So let's see, where are some oh, we've got water, so we could have this half reaction. We've got potassium iodide. There's some iodide. We could have that half reaction happening. Anything else involved? Oh, there's another water reaction. And potassium, anything with, oh, there we go, there's the potassium, K+. So those are the 4 possible half reactions that we could have. So now, let's look, I've got those written down over here. 4 possible half reactions. And now we have to figure out, well, which ones are the ones that actually happen? We need the most positive E0, even though overall E0 will be negative. Now, the reactants, we have to have the reactants available to react. We don't have oxygen in the system. We don't have iodine. We have potassium ion, iodide ion, and water. So we have water, we have iodide ion. So these first 2 reactions could not go in the forward direction because we don't have these reactants available. They can only occur in the reverse direction. So we would change the signs of the E0s, and we pick the least negative. This reaction gives us the least negative. So that will be one of our half reactions. The other 2 reactions we do not reverse. We have to pick which one it will be. And between these 2, this one is more positive or less negative. So that will be our reduction reaction. This one will happen at the cathode. This will be our oxidation because we're reversing it. It will happen at the anode. I hope I said this will happen at the cathode, reduction at the cathode. And here's our overall balanced reaction and our E cell. Okay, one more problem, and then we're done. Okay, so this time we've got copper 2 iodide. Again, we have to figure out what are the possible half reactions that could occur. So you better take out your standard cell reduction potential sheet. Pause this now if you don't have it yet. We've got copper 2 iodide, so we're looking for anything that has copper 2 in it. Oh, there's one, there's one. Copper 2 or iodide. Oh, I see an iodide. Or water. There's a water. And you should have out your standard reduction potential. I don't know where that came from, but ignore it. Here's our water. Okay, we have 5 possible reactions now. And again, you look at your standard reduction potential sheet, and you check which possible reactions could occur given what's sitting in the solution. We have 5 possible reactions here. This should say E0 up here. I need to fix that. Okay, of these reactions, there's water, there's iodide, there's copper 2, and there's water. So these reactions could occur in the forward direction. These 2 would have to occur in the reverse direction because I only have these available. I do not have any of these. So between those first 2 reactions, when I reverse them, the iodide reaction gives me a less negative, more positive. So this will be my oxidation reaction occurring in the anode. Of these 3, the copper 2 to copper gives me the most positive E0, so this will be my reduction reaction. And this is just a summary of what I said. Oh, the overall cell reaction, pause this if you want to calculate it yourself. I reversed one of the reactions, and the overall balanced reaction, we are done.